So, hello everyone and welcome now to our last session of our Digital V-Days. So yeah, for us the final session, and we are very happy that you took your time today, this afternoon, to take part at our session. I'm very happy to welcome also you, Kristen, to be here in our webinar. So yeah, Kristen Morgensen is working at Texas Instruments, and he's presenting our topic today, EMC and EMI optimizations in single pair Ethernet for industrial communication. So just a few words from myself in the beginning, a few information. So you will be muted during this webinar. This means that you cannot ask us your questions via the microphone, but just send them us in the chat, and then we will, after the presentation, go through them. And yeah, if we don't have the time for them, then we will contact you via email afterwards. We will also share at the end the slides of the presentation you will see, and also you will get the link to the recording in the next few days from us. So that's enough from my side. Kristen, then have fun and yeah, enjoy the webinar.
Yeah, thank you. So today I wanted to present the topic EMC EMI optimization for single twisted pair Ethernet. But in general, it's also showing what are some of the key things you need to think of when you look at single twisted pair Ethernet to ensure that this will work in the industrial environment. And of course, there are some things you need to consider when you do this. And this is what I will show today. So just a quick walkthrough of the agenda. So the agenda is basically, we talk a little bit on single twisted pair Ethernet in general. So you see what is it? And then we are showing what are some of the key things you need to do to actually achieve the capability of using it in an industrial system. And then of course, going into some of the key points where you see single twisted pair Ethernet is very nice and has very good features that make sense for industrial purposes. And then of course, looking at the overall descriptions, but also some of the next steps that we have done and we are planning to do for the future, doing these initial investigations. Now, first going through single twisted pair Ethernet. So as Ethernet also, as you know, basically there are the 10 megabit, the 100 megabit, and the gigabit single twisted pair Ethernet. What we will be focusing on today is going to be the 100 and the gigabit single twisted pair Ethernet. We have, however, also done some measurements and other contents on the 10 megabit Ethernet. However, this we will not walk through today. Another point to see with the single twisted pair Ethernet is looking at what are the actual distances that you can achieve from a cable perspective when you use this technology. And this you need to take as it's one of the limitations that you need to be aware of before you start developing your system, that the system will work as intended. What the PHYs that we are working with today is basically the 10 megabit, so the 812 PHY. This is already available on ti.com. So if you search this part number, you can find it on ti.com and read the data sheet, get more information. What you also see here is that this PHY has multiple MAC interfaces. So you can basically choose which kind of connection do you want to use. A second PHY that we'll be talking about today is the 720 PHY. This 720 PHY we also have on ti.com. And if you take this part number and you put it in the browser, you can also find it, and you are able to look at this. Again, here, these two PHYs, they are not pin-to-pin compatible, but very close to. So the board that you will see we have built, you are basically able to take either one PHY or the other PHY, replace some passive components, and you can test both systems with one board. Now, looking at the actual board that we have built, we have actually built this single twisted pair Ethernet board There are some key points we have done with the board, but also another key point we did was we added it with the Citaura processor, so the AM64 processor. This processor basically enables you to also have a real-time MAC interface. This real-time MAC interface we also use to show single twisted pair Ethernet in an industrial communication system showing real-time capability. This we have already implemented, and we actually showed that at the Würth booth at Embedded World. So here, if you're interested, we also have more information coming in this direction that we'll be gathering in the coming time. But what we also did, which is more important for today, is basically taking this board and saying, is this ready, and is the technology ready to actually do pass the industrial requirement on EMC and EMI? And a second point on this board is also we are working on actually getting this on ti.com so you can buy it. This is not available right now, but we plan, and I say plan, to have this within the next, I would say, maybe 2 to 3 months. Now looking at the content and some of the key points to actually look at. So some of the key parameters is for industrial purpose is also say, hey, why do I care about EMC immunity? And I think one key point is very simple. If you look at the motor, if you look at motors in an industrial floor, if you have high voltage motors, these motors typically get controlled with PWM signals where they have a very high slew rate. This high slew rate will basically influence all the communication lines. And you need to ensure that this influence of communication line doesn't destroy your communication. So you're actually still able to communicate while the motor is turning. And what you also see here is a little bit of showing what it looks like, this noise. A second point also to say is this noise can also be coupled on the power port. And this is why when you do EMC measurements, you both test the cable, but you also test the power port for noise immunity. And when we do the testing, what you see is the cables here and also where the noise sources are. And of course, this is why you have the industrial testing, is simply to be able to say, before you put your system on the market, is it noise robust and can it actually do what I intended it to do without failing during as soon as I put it in the real environment. Now, looking at the EMC requirements, what we did was we looked at the motor drive standard, and here there is a nice table showing the requirements of the standard for the EMC measurements. What you also see is this definition around criterion A, criterion B, and criterion C. So what you see is that if you actually look at the test will actually accept if you have a criterion B, meaning temporarily the system cannot work, and as soon as you stop the test and the system automatically goes back into a functioning state, this is okay for the test. But of course, in an industrial system, if you don't have any communication to the motor for a specific time window, this is not okay on a system level. So of course you need to show how can I do criterion A when I'm doing these tests, because that's the only measurement that's important. What you see and what you also see is that, of course, here the class C, this is the one where you need to power cycle the system. And of course, this is for industrial systems a complete no-go. Now, what we did was we actually built a test setup based on the Citaura processor plus this board we built, the PHY board, where we can actually show that do we lose a package, and also we have added some additional features that we are actually able to show inside the package which bit got the failure, and we can do analysis and understand this system, and also this helps us, let's say, develop a very robust system, so to say, in the end. Now, looking at some of the coupling concepts that you have for single twisted pair, and I think this is also a key point to be aware of. You have the capability of saying, I'm building a capacitive data coupling circuit. This data coupling circuit is typically what you will see when you look at it from the automotive perspective. This coupling brings some benefits, but also some negatives. One of the negatives is that when you have this capacitive coupling cap, the cap rating will define your isolation voltage. And typically when you're building an industrial system, you need to have 1.5 kilovolt rated isolation, meaning you need to take a cap which has high enough isolation rating. So you see the size will start to go up a lot. Now, a second thing we're seeing is that these capacitors are working nicely, but as soon as you start adding these high slew rate noise that I mentioned before from the high voltage motors, this high slew rate noise will actually saturate the cap, and suddenly you have no link on your single twisted pair Ethernet. So what we did when we realized it was we said, hey, let's look at the galvanic option, where we also worked with Würth, and we tested their transformer that you see here. And with this transformer, we, for free, get the 1.5 kilovolt rated rating. But also now the system is more noise robust, so we can actually pass the testing for this IEC measurements that I also mentioned before, which basically kind of show now the system is not just a theoretical good idea, it's actually starting to be ready to be put into the industrial systems. And we already see that this trend seems to be moving slowly in this direction. I'm not saying it's going to replace standard Ethernet, but there are definitely some areas inside the industrial floor where single twisted pair makes more sense than staying with the standard Ethernet. And this is where we are working with Würth, but also with our customers to try and find where are these places where it makes sense, and let's help you understand how can we make the system work. And a second thing that's also very interesting I found was the discussion around the size. What you see here is, this is the size if you only look at the components that you put on the board on the coupling. And it's actually smaller to take the galvanic option than it is to take a capacitive option because of the common mode termination that you need to put on the system. So, and there is a lot of assumptions saying the capacitive coupling is smaller. This is by numbers. You see the math. It's not the case. And also size-wise, height-wise, it's a very small difference, which I would say you can almost ignore it. Now, looking at the inductive coupling, what you see the example of the common mode choke, but also the transformer we use. Basically, you see them here for the 100 base T1, but also for the gigabit base T1. Here, what you can also do is simply take the gigabit one and use them for both the 100 and the gigabit version, and you can have one board with the small updates around the PHY, and you can pick either 100 or gigabit without building a new system, so to say. Now, looking at some of the tests we did when we started to do the learning of how does the system work and how noise robust is the system. So what we did was here, we built a test system where you can see that system here. This is basically a high voltage motor drive where I can tune the DC link, and I can tune it up to 1000 volt. And this cable is basically this hybrid cable you see here. And they basically have one twisted pair, a shielded twisted pair inside the cable, and then it also have the motor windings inside. So we are able to basically say we do a 20-meter cable test, we put the noise from the motor, and we put it on a system where we put the data communication of the single twisted pair. And what we saw here was that, as you see here, I think it was around maybe 120 volt, we started to see the link drops. And as soon as we saw the link drops, basically it continued, of course, with the higher voltages. As soon as we did the system new and tested it with the galvanic coupling, basically you see all the errors disappeared. So there is no errors up to 500 volt. I didn't test it higher than this because of a limit of my power supply. However, I could have tested it on a system level, but nobody required it. What we also did from this point on, we moved in and did the EFT test instead. So we took the cable, put it in an EFT clamp that we will see in a later time. And here we could test up to 4 kilovolt or 5 kilovolt with the EFT clamp. And we deemed this is a better choice of the testing. Now, what you also see here with industrial compliance testing, and this we did in collaboration with Würth here also, and thank you Würth for helping us doing all these tests. So what we see here is that we have the EFT testing where you see the capacitive clamp. We also tested the EFT testing on the power supply. Also we did conducted RF, we did surge testing. Actually here with the surge testing our first board, we actually realized that we did some layout updates. So we actually have a second revision already on the board. And here we actually blew up some wires during the 4 kilovolt surge when we did the testing. The PHY was still linked, but the board was destroyed. A second thing also to see, we did the ESD testing where we did contact and air discharge. And of course, we also did the SPE testing, so the EMI testing, where we also wanted to show is what are the key care abouts on a PCB level to ensure that you are ready to pass the testing you need to get your system to the market. Again here, looking at the immunity test from before, but also here you see some of the results we did on the testing and where you see we passed and not passed. But what you see here with the yellow is basically we didn't go to the double the tested rating. It's lower, but you see that for the actual rated level, we are actually class A. One of the things we also see here as a problem of the system that we were testing is that the processor board we had, it is not EMC optimized, meaning this is causing us some issues when we are testing on a system level, everything. And there are some things on that board that needs to be updated. And of course, this is also something we're sharing with you when you're starting to look on building your system. A second thing is also looking at the EMI requirements where we tested for the SPE, I think it says here 32, but we also tested the SPE 11. And here also we see that we are passing with a 6 dB margin on as the lowest margin on system level. Now, one thing I also wanted to show is to show the measurements around on a system level when you look at the results here. So what we did with the testing was we did a update here where we did the board, and with the board we did the measurement. I see that for whatever reason there is these pictures here. It's gonna be shown on the other slide. So basically the end test we did was we passed here. This is with the original boards as we built them and also the first revision. Now what we did after the testing, and you can see here, after we tested it, we actually did all these kind of updates on the boards. And with those updates, we were able to pass the testing. But here you see, this is the initial measurements we got where you see all the faulty measurements and where we also see this is where some of the, let's say, places where we didn't pass the measurement that we basically know, well, this is the RGMII interface that's not correctly done. This is again the third harmonic of the RGMII interface, and this is basically the power supply ringing that you see when the switching is having the overshoot and it's ringing down. That's the errors we see here. But as soon as we got those under control, we were able to show on a system level everything is below the tested rating. Now, also what I wanted to show is from a layout perspective, of course, this is the first test. What you see here, that these traces here, they were basically too thin to hold the surge current. So what we saw were they blew up when we went high enough in the surge. And that's why you see on the second version, I did a polygon plane, which I should have done in the first place, but I didn't. But we know now why I should do it. And you see the polygon plane, but this board here, we have done in Altium. And of course, this board is also something where we put it on ti.com, and you'll be able to download it as soon as the board is on the webpage. If you're interested to get it earlier, you can write us and we can try and figure out how to share it earlier. Now, that's basically part of the EMI, EMC measurements. There are also some other very cool features within the PHYs that makes them very interesting for industrial systems. Now, looking again here, you see here the system here with the EMC, EMI measurement. One thing that I wanted to quickly mention on it is the PHY also have some capabilities to do diagnostics inside the PHY that you can read out on the serial management interface. This system here will basically enable you to do it can help you do predictive maintenance. And this basically is a very nice feature to help you achieve better performance, but also make it easier for you to do to not have to do emergency shutdown on a system level, so to say. A second thing also, I mentioned it a little bit before, we also have a measurement showing that the single twisted pair PHY and also MAC layer, if you built it up correctly, it is ready for real-time communication. You can achieve it. We have measurements that we can share, and we will also be sharing that shortly to try and go through all these small points that you need to understand to actually get to the point where you can say, single twisted pair, I believe it. I think it makes sense for me in these and these systems in my industrial floor. It will not be everywhere, but there are definitely places where it makes a lot of sense. And this is also what we see with the interest that we see from a lot of customers, but also some of the prototypes we already see are available today. And with that, quickly going back to the conclusion of single twisted pair Ethernet is happening. We see there is a lot of interest on the topic. I would say now, don't just stay interested, start working with it. It's definitely happening. You can see with the measurement we have shown, it is ready to be put in industrial environments. You need to know some of the key care abouts on a system level to understand where it fits you. But at the end of the day, you can do all the testing and also build the system in a way that you can pass all the industrial requirements that are needed to do it. Another thing that's also very important to understand on, but I didn't touch it here today, is the latency on single twisted pair Ethernet. This latency is a lot higher than you are used to with standard Ethernet. And of course, you need to understand this when you want to build your system. And of course, here we have TI has basically done all these testing and also in collaboration with Würth to basically support the customers to better understand how can I use this system. And of course, here we are also very interested in questions or feedback on what potentially questions do you have before you're starting to say, well, it's not just the theory anymore. I actually want to start working with it. And with that, thank you for listening and continue and have a continuous nice day or evening or morning.
Exactly. Kristen, thank you very much for your very interesting presentation. And this presentation you can now download. And I see the first ones of you are already downloading it. So feel free there. And then I would say, as you already said, it's time for the questions and we are heading right into the first ones. So this is the first question. Sorry, I will place it here in the middle of us. Slide EMI results.
So the first question here, the slide for the EMI results. You are correct. What we did actually was we actually removed the foil. Then we put the earth or the ground plane on this copper foil to really try and say, what are the key problem points and how, do we understand correctly what the real problem is? That when we change the layout, we can actually we actually know that this change will actually solve the problem that we were seeing on the measurement.
Okay, thank you very much. So then next question here, apart from IEC 61803, have you also tested against standards with requirements for higher levels of immunity? For example, functional safety industrial environment standards, like those norms here.
So at the end of the day, we focused on the test here. However, the results, and also if you see the results we did, you can actually see we tested also pretty much always up to double the standard. However, what we saw there was some of the results were, there are some things where we need to go back with Würth and do more tests with the new board. It's something we have on our radar and plans that we need to do. Yeah, not hopefully, the boards are ready. We just need to figure out a time to go test. So it's on my to-do list. And then the second point is that the EVM that we use is basically also, we know this has some limitations and this will definitely also cause some issues with it. However, we know if you want to go on a system level, that how to let's say prevent this when you build your system for your environment. And also, if you look at functional safety in general from a single twisted pair Ethernet perspective, the single twisted pair Ethernet is part of the black channel. So what you need to think of is you need to have the additional bandwidth in the processor and the additional bandwidth on the communication line to have the additional data that you need to actually achieve your functional safety requirement. So I would say from a functional safety perspective, I don't see why it shouldn't work with all the other measurements we have done.
Okay, Kristen, thank you very much for that answer. Then, let's just move on with the next questions. I see there are a lot of questions coming in. If we can't answer them all today, then we will answer them later on via email. So then, do you pass with galvanic coupling TCB?
To be very honest, I'm not sure I'm understanding this question. So if you can write a little bit more details what you mean, I will definitely would like to come back with you on it. I'm sorry, I'm not. It's a little bit too short to understand that I understand what the question is asked.
Yeah, maybe our attendee here. Okay. So we hear there is already something else. So additional info. I just have to get it right here. The Open Alliance TCB. TC8.
Yeah,
sorry.
TC8. To be honest, I don't know that test, to be very honest about it, but it's definitely something, if we understand it in more detail, we will look it up now after the meeting. It's something we would be very interested. At the end of the day, we want to show that it works in these industrial environments, that you also have a good feel for, does it make sense for me to try? So all these questions is something we will be looking into in the future.
Okay, thank you very much. So then next question is this one. This one, yeah.
So this question at the end of the day, when I say the pass-fail criteria, what we did was the processor we used, we built a system software where we can send a predefined data package with a counter in it. So we know if we lose a frame, how many frames do we lose in a row. We also have the capability to detect this data frame loss and then save the wrong data in the memory. It's not thrown away. We can actually save it in memory later. And we know exactly what the data is supposed to be sending. So we can go back and test what's the actually bit flip problem that we see on this package. But this is a own software that we did for all these test purposes because we see this EMC, EMI testing in a lot of different systems, like for standard Ethernet, for single twisted pair Ethernet, for CAN, RS485, and all these systems where we needed to build a test setup to show a system performance on that made sense. Also looking at it from an industrial perspective. The test system we did, we can test the bandwidth up to 100%. So we are able to send continuous package. The only limit we have on it is there is an inter-package gap between the different packages, but that's the only point where we don't send data. The rest of it is continuous data. We can vary it. Do we send it for 15 kilohertz, 16 kilohertz, or 30 kilohertz? Sky's the limit. The software can be updated to fit all kinds of things.
Okay, yeah, that sounds nice. Okay, thank you very much, Kristen. Then next question: what real-time parameters are possible using single pair Ethernet? What is the latency also and jitter that can be achieved?
So if you look in the datasheet, we actually documented these parameters inside the datasheet. So you can actually read it already if you go into the datasheet that I mentioned on the PHYs before. However, for the gigabit PHY, the total latency is either 1 microsecond or 8 microseconds. And this depends because inside the PHY, there is a Reed-Solomon encoder. This Reed-Solomon encoder is basically giving you forward error correction, but it adds an additional 7 microseconds of delay inside the PHY before the data is passed back and forth. If you want, you can disable this feature and then you will go down to the 1 microsecond. What we showed at Würth is basically at the Würth booth, but also we have video of this demo, is we show a single twist pair real-time system on gigabit, and here we are showing cycle times down to 10 microseconds. So you can do it very, very fast, and also with the real-time MAC where we show it, the jitter there is within, I would say it was within 10 nanoseconds we were able to achieve with the real-time MAC that we used for our test purposes.
Okay, thank you very much. So then the next question or answer is referring to a question we already had. So this is to this one about the lower power supply region.
So the copper you see there was actually done more to shield the communication lines. The power supply ringing we saw, that was from the EVM board. This EVM board, we looked at it, it has very big current loops on the power supply, and this is causing ringing. Of course, we could have spent some time on it with Würth doing EMI filters and all kinds of stuff, but at the end of the day, that layout is not optimal. We would also need to change the layout, and this is something where we are considering to say we are removing this piece and adding some type of additional power supply on it, but it's something where we haven't really figured out a good way to actually show it with this board, or potentially even saying we need to build a EMI-ready test board. We are still investigating this, but at the end of the day, we have done an app note where we are describing what to think of when you do power supplies. If you search on Google on my last name, but also my colleague Stefan Graf and EMC, EMI, you will find this app note. And here we are explaining in more detail some of the key care-abouts around the power supply, but also the clocking, and we are planning to update this to also add the data communication lines on it.
Okay, thank you very much. Then, we will just go on with your questions. Very nice to see all that feedback from you. So here question, any documents for latency calculation? As I know for automotive, this latency are very small. Otherwise, it is very critical in automotive environment, right?
To my understanding, industrial is more requiring than automotive in both. The only thing maybe not is EMI. EMC is a lot more requiring for industrial. Latency-wise, it's a lot more requiring for industrial purposes than it is on the automotive side. What I've seen from the questions I get from customers, but also what I've seen been implemented with the automotive systems. There may be, let's say, it may be the typical things I've seen. I've not seen some special corner cases, but at least what I've seen, it's more difficult to do the industrial stuff than it is to do the automotive things.
Okay.
But one question on the latency. We have actually done an app note on this. If you search on Google my name plus single twisted pair Ethernet, you should find an app note where I go on some of the key points around that you need to consider when you are starting to evaluate single twisted pair for industrial purposes. And here I'm going through latency, EMC, EMI, not to the detail of the presentation here today. I want to update that app note with the data that you see here. And then also, but here also I'm going through a little bit more detail on this diagnostic features that is inside the FI that can help you. And it's a pretty good guide giving you some good ideas what to think of and what some of the key care-abouts that you need to consider when you're building these systems.
Okay, thank you very much. Then the next question is from the same attendee. To improve the RGMI, which type of care have you done in layout? Or is this something related to drive strength?
At the end of the day, we took very special care in layout to do length matching, impedance matching on the system. Also, the connector we chose is impedance matched. If you do the pin mapping on the connector correct, which was not done on the EVM board details again, but we were basically able to do some tricks on it with this copper foil to improve here. But we also want to document this in this EMI EMC measurement report as a next step. However, key points is length matching, impedance matching on the traces, ensuring that you have termination on RGMII pending. Is the termination integrated in the PHY? Is it integrated in the MAC? Ensuring it's located on the right position pending where the TX RX is. All these things you need to consider, and yes, we took care of this, and we also show it in the EVM we did.
Okay, so then for now, I see the last question here. So, what is the price difference between C and galvanic coupling?
So I actually asked Würth this question. The numbers I got is probably a year old, so maybe they're a little bit off. But the question is actually, and I normalized it. So if you look at the capacitive coupling, either the 100 kilovolt cap or the 100 volt cap, it would be around 0.6, 0.5 in that point, where the galvanic coupling would be 1. So roughly a 30-35% increase. However, you gain for free a smaller PCB size and a lot more robust system because the transformer is actually optimized for the signal rate or the frequencies that you use. This is not necessarily the case for the caps you use.
Okay, so then I think we are already finished with this webinar, and that's also the end of our digital V-Days. So Kristen, thank you very much for your session today.
Thank you for inviting me.
Yeah, for all the information and the answers to the questions. And then I would say also thank you very much for your attention.